Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. My name is Lisa Green, and there we go. Good morning. My name is Lisa Green, and I'm from Science Commons. I'm really excited to be here today. I hope you are too. And if you're not, I'm sure you're going to be once we get started. We have a spectacular lineup of speakers, and the things we're going to be talking about today, I mean, these are some of the most important ideas in science right now, and their impact goes well beyond even science. So I'm really excited, and I'm sure this is going to be a very stimulating and rewarding day. Before we get started, I'd like to give out some thank yous. And my first thank you goes to my co-organizer, Hope Lehman. Many of you know Hope. If you don't know Hope, I encourage you to introduce yourself to her today and thank her for this day, because it's not hyperbole to say we wouldn't be here without Hope's work. So thank you very much, Hope. Also, I want to thank our video blogger, Chris Perillo. Chris has a tremendous following, and he's really helping us get the message out to as many people as possible. It's being live cast now, and it'll be packaged so you can download and watch it again after the fact. And the biggest thank you of all goes to Microsoft Research and Lee Dirks. Microsoft Research is a longtime supporter and partner of Creative Commons, and they're a source of innovation for over 2 decades. And speaking of who we wouldn't be here without, Microsoft Research is who really made this happen. Lee is who really made this happen. I would get emails from Lee at 2 in the morning and then again at 5:30 in the morning. So he had a lot of passion about making this happen, and we're really grateful. Later today, pretty soon, you'll hear Peter Murray-Russ speak a little bit about what's going on at Microsoft Research with his collaboration. But right now, I'd like to bring up Lee and give him a very warm thank you from all of us, and he's going to tell us about what's going on at Microsoft Research. Lee?
Okay, so I do send emails at weird hours. There's no doubt about that. But it's definitely Lisa and a lot of people from Microsoft Research that made this happen. It certainly wasn't me by myself by any stretch of imagination. But my name is Lee Dirks. I'm from Microsoft Research, specifically a team called External Research. And I'm going to speak a little bit about that in a moment, some very brief comments. But first off, thank you all very, very much for coming out bright and early on a Saturday morning. It's a tremendous day, so I'm very sorry to lock you in a room, but we have, in conjunction with Lisa, lined up an amazing group of speakers. So I drove all the way from Seattle to see them. Sorry, I don't know about you guys, but no. But many people have flown in. Obviously, some of the speakers are here from the UK, so it's a tremendous occasion, and I think it's going to be very, very exciting. There's some things that were announced yesterday that I think will be delved into today that are going to be of interest to everyone. So an auspicious milestone. But I'll leave it to the speakers to chat about that. I did want to cover a few logistics for the day. First off, wireless. Everyone, if you don't have the wireless code, it's written up here. We also have slips of paper at the registration desk. So if you need to get access to your internet, that we should have no problem. If there's any problem, do let me know. Track me down anytime during the day and let me know. Chris, as Lisa mentioned, Chris is live streaming this, so that's available right now. In addition, Microsoft Research is going to be taping and capturing the entire day. We have a kind of a relationship with the University of Washington and a research channel that we put a lot of our talks out on. So this will be made available after the fact, and we can send a link out. So this whole day will be captured, and you can definitely share that with everyone. So the speakers have all signed release forms, except for the 2 I haven't been able to track down yet. So if you are a speaker who hasn't signed a form yet, come find me. But that will be available. We also will be having a reception at the end of the day. So at 5 p.m. Until about 6:30, out in the atrium of Building 99, we'll have a wine and cheese reception. Everyone is welcome to join. Also, at that time, we will be giving everyone free copies of The Fourth Paradigm, which is a book that Microsoft released in October that is related to kind of the future of e-science. And it was we're very proud to say Microsoft's first Creative Commons release publication. So all of the content is openly available, thanks to obviously to all the authors for making that available. But I do have a copy just to show you what it looks like. So everyone will be getting a copy of that. And yes, there's the Creative Commons license right there. So everyone will be getting copies of this. And we've got a commitment from John Wilbanks. He was one of the authors of one of the articles that he'll do book signings. He said, if people want my signature, I'm happy to give it to them. So pin him down, okay? The other kind of logistical point is obviously this is a Microsoft building, and we're not normally open to the public on Saturday. So I think many of you have dealt with the security guard to get in. We need you to kind of stay in this area. This is a public area, but if you need anything, again, come to me or come find the security guard. If you get outside of the building or something like that, knock. The security guard should be there all day. But if you get locked out, knock and wave at him. And restrooms, hopefully you found them down that direction. There's going to be refreshments all day on the back. We have a box lunch for you, and then again the reception. If you need other beverages other than the ones that are provided here, outside of this hallway and in the back corner, you can actually go out through either of these doors as well. There's a refrigerator with a selection of beverages there as well. So if you need a water or Coke or a little caffeine to keep you up, so you'll find that. Perhaps some of you are saying, wait a minute, what does Microsoft Research have to do, or why are they interested in Creative Commons or Science Commons? And so I wanted to give a little bit of context. Our legal team has been working very closely with Creative Commons for many years. So Tom Rubin and Lawrence Lessig go back a ways, and so we've had a long-standing relationship with Creative Commons overall. But mainly over the last probably 3 or 4 years, Microsoft Research and External Research has developed a relationship with Science Commons. And what I wanted to do is go ahead and give you some background. So Microsoft Research overall is in a group of about 900 researchers. About 450 of them reside in this building, and the remainder sit in these locations around the world. Research, as Lisa made reference to, has been around for almost 20 years. We'll be celebrating our 20th anniversary shortly. And we and look at in all areas of computer science, but specifically our group is called, that we reside in, is referred to as external research. And so our team is very focused on applications of computer science, and specifically applications of computer science in health and well-being, in core computer science, in earth, energy, and environment, and then the area that I'm responsible for, which is education and scholarly communication. And so we look at the applications of computer science in those areas, and our team is called external research because our team doesn't do the research here. We do research in collaboration with external parties, typically, most often with academics, and you'll see 1 or 2 examples of that over the course of the day, some of the projects that we have going on. But we've done a couple of partnerships with Creative Commons that I just wanted to reference, specifically out of my group. One of which some of you might be familiar with. We actually, about 2 years ago, released an add-in for Microsoft Office, which allows you to embed the Creative Commons, let me go back there for a second, the Creative Commons license in either PowerPoint, Excel, or Word. This is actually one of our most popular downloads. We've had something over 500,000 downloads of this add-in alone. Another one that we did about 1.5 years ago was the ontology add-in. We originally did this work with Phil Bourne at University of California, San Diego, and then we actually did some work with John Wilbanks and his team that is responsible for NeuroCommons. So this is an ontology add-in that allows you to import any ontology. Whoops. It's on a timer. Shouldn't be. Sorry about that. That allows you to import and embed an ontology into the Word document, have that travel, and then mark up specific words in XML and embed those tags in the document itself. So just a couple of examples of the engagements that we've had. What I would like to do now, just to give you a little bit of context, but what I'd like to do now is actually turn it over to my colleagues, Stuart Tansley and Tolle, and they were going to go into a little bit more detail about the fourth paradigm. And I think this is if you're not familiar with it, I think you'll find it an intriguing book. And I think, again, John's got an article in it, but there's a lot of similar concepts that I think we'll be addressing today that were addressed in this book. And so I'd like to hand it over to Chris and Stuart.
Thanks, Lee. Those of us who, Tony Hay, who is the actual main editor of this book, and is also the vice president for external research, likes to describe himself as somebody who practices management by walking around. Those of us that know Tony a lot better and work with him actually would say that Tony likes to first send out an email, let's go do crazy idea X, and then he wanders around trying to find out why nobody responded. And that's pretty much actually how the fourth paradigm started out. He really wanted to create a book that would show how computer science was facilitating each of the pillars inside of his external research team. And those pillars are health and well-being, their scholarly communications, earth, energy, and environment, and then core computer science. And the book itself is actually structured this way. It has these 4 different themes. Now, there was one person who actually responded to the mail and said, here's a list of authors I think would be really good, because she'd already been thinking about creating a similar book, but just localizing it to health and well-being, and that person actually happened to be me. And so once that mail hit his door, you could almost hear the elephant-like footsteps pounding their way down to my office saying, you think this is a good idea? We should do this? And of course I agreed. So a book was born. From the beginning, we had 3 tenets that we wanted to make sure that we hit. And the first tenet was that we wanted this book to honor Jim Gray and his memory and the good work that he did. Secondly, we wanted to illustrate how it was that science was really transforming, computer science was actually transforming science, and how it was dealing with the deluge of data that we deal with every day. And lastly, we wanted to make sure that this would be openly and freely available to everyone, because we thought Jim really would have wanted it to be that way. So since I had already had my list, then the next challenge was for us to go around to each of the other pillars and collect those lists. And then we got down to the real core business of writing a book. And I won't go into detail because I'm sure many of you know what it's like to edit a book. It's a considerable amount of effort and a considerable amount of challenge. And so along the way, we picked up Stuart. And believe me, Stuart was a godsend. Not only was he helpful with the day-to-day stuff, but he also brought a very unique perspective to the book. He brought the perspective of how do we get there from here? So that's useful in the day-to-day work where you're having to collect papers, get them back, get them edited, send them back, go through review. But more importantly, he brought the perspective of how you think of the book as a whole, and then you move that into the space where people could actually make it actionable. And so he really helped us see how we could take this book forward and make sure that it remained a living document, that it would be something that would be owned by the community. Stuart?
Thank you, Chris. It's kind of you. We're Microsoft too, right? We're Microsoft too. So I've got my slides. I thought I'd show you some slides too. Thank you for the introduction, Chris. I'll press the right keyboard first. What is this book in terms of the gritty detail? It's 250 pages there. You've seen a copy. You'll get a copy later if you so wish. The book. It's the first Creative Commons publication from Microsoft Research, which we're really proud of. As Lee said, it took us a while to get there. We've been working with Creative Commons for a number of years. But this has really been a breakthrough, and we hope to see other publications come from Microsoft Research. It's an edited collection of 26 papers, short technical papers, just 2,000 words on average. There was some editing involved.
Some editing.
There's about 70 leading practitioners from around the world. Many of the names I hope you'll recognize. A few you may not recognize, but we think that you will recognize them in the years to come. It's not all Microsoft, but there's significant Microsoft. But it's mostly not Microsoft people. It's published under Microsoft Research, but mostly it's about 45 authors, scientists, and some computer scientists from around the world. The 4 themes I won't go into again, we've highlighted that. And just to reiterate, our own external research group is somewhat structured along similar lines because it maps how we think this field is panning out. Jim Gray, who, together with Alex Tolle and Tony Hay, really formulated this concept of the 4th paradigm. There's some hints about the other 3 paradigms, if you're not familiar with this, at the bottom of this page. It really was a testament to Jim inspired us all who interacted with him. And there is a certain labour of love. Chris was very keen to even use that phrase in the book. We're very proud to represent Jim's legacy going forward, but as a living entity, not as something that just as a milestone. This is something that Jim would like to have seen going forward as an idea, a meme in the community. We launched in the eScience workshop. I hope you're familiar with that workshop in October. And let me show you the cover. You've seen that. We've got that. Doesn't have the Creative Commons license on. This was a pre-publication version, but I assure you it is on the real one. I won't have time to go through all of the details, but here I do put up some of the papers. You see, we have structured it in the 4 sections as being described, and you'll recognise some of the names already there. Next page, I think John is highlighted on this page, bottom right. Yes, no?
Yes.
Yep, good. And so without further ado, that's what it looks like inside. I hope you enjoyed the book. You can get to it from this URL. If you don't want to carry a heavy copy home, if you've travelled a long way, it's downloadable too. But it's printed nicely, so do take a copy for yourself. Okay, thank you very much.
Very good, and with no further ado, one bit of ado, sorry. I did want to pass along regrets from Tony Hay. Dr. Tony Hay was unable to be here today. It was something he was very passionate, very much intended and wanted to be here. Unfortunately, he had this pesky event that he was being awarded a fellow in the AAAS today in San Diego. So he had a conflict, and so we decided we'd let him go on for that. So he definitely does wish he could be here, and passes on his regards. So now, with no further ado, I would like to hand the podium over to Dr. Cameron Neylon, and he will be speaking to us about science in the open. Why do we need it, and how do we do it?
Okay, so am I amplified yet? Or do I just need to talk loudly? We'll see how we manage. So thank you again to Hope, Lisa and Lee for the invitation to come, to Hope in particular for emailing me, I think about once every 12 hours over a period of a couple of weeks ago, saying, are you coming? Have you sorted the logistics yet? And thank you for our hosts, and thank you all for coming. I put this slide up hopefully to somewhat frame the point of today's discussion. I should add you are also free to take notes, to think and to disagree with me, and indeed to publish that. But while I'm thanking people, I want to thank a whole bunch of people. And this is actually, for those of you who've seen the slide before, I've actually updated it now, so it's not quite as out of date as it used to be. If I have seen any distance at all, it is by standing on the blog posts, the tweets, and indeed on the formal publications of others. We would do well as scientists to remember that... Oops, it's coming back. We would do well to remember that even the biggest paradigm shifts, the biggest breakthroughs in science are really a very thin veneer over what has come before. And sometimes a little humility perhaps might be effectively applied to the process of how we think about communicating science and how we manage it. A lot of the people up here are not necessarily people I've met. Some of them are people I've met online. Many of them are people I disagree with profoundly. But they're people who've influenced my thinking, and to a very large extent I can no longer tell which of the ideas I'm presenting are my ideas and which have come out of these. Think of this more as me filtering the things that I've seen, though you shouldn't hold these people responsible for what I'm saying, obviously. Okay, so who am I? I live in Bath, which is a lovely place to live, and I work at a place called the Rutherford Appleton Lab, which happens to be about 60 miles away, so I have about a 2-hour commute each day. The organisation I work for is called STFC. We're a UK infrastructure organisation. However, we are also a research funder, so I need to put up this disclaimer saying that I'm not presenting any policy here of the organisation, blah, 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 blah. So I get up relatively early in the morning, unfortunately, and I catch a train, and then I get on a bus, and then eventually I get to work, usually about 8:45 in the morning. The things I work on are more or less could be described as structural biology. So we're talking about trying to determine the structures of biological molecules, and in particular I'm interested in trying to solve the structures of assemblies of biological molecules using a range of techniques, but primarily small angle scattering for those who are interested. I can witter on about that for several hours, but I will avoid doing so at this stage. I also get to do a lot of really cool experiments. We do some stuff with protein labelling and connecting proteins to other stuff, so we get to take cool pictures of fluorescent stuff, which is always a lot of fun. It's an interesting mixture of small lab work, so this is actually a picture of me in the lab, and also I work at a large facility, so we do experiments that kind of do involve the big iron of experimental facilities, but also we have some experience of the problems of handling and looking after data. As a scientist, you spend an awful lot of your time reading, you spend an awful lot of your time in meetings, and probably too much time travelling. This is my second home, the departure terminal at Heathrow Terminal 5. Often I'm doing that to give a talk, which usually involves me preparing the talk at the last minute, often on a Saturday morning. Which I should say, for those of you following along at home, you can find the slides to a similar talk at slideshare.net/Cameron-Neylon. They're not quite the same slides, but most of them are there. So I show a picture of myself in the lab, but often the students are actually quite keen to keep me out of the lab. This was not actually my fault, but these kind of things do happen. And of course, these lead to more meetings about safety and then more stuff about more reading. But at the end of the day, I get on my bus and I go home, unless, of course, I'm travelling somewhere. So the question one might ask about this kind of lifestyle, the lifestyle that many scientists choose to lead, is why? And there are a series of levels to this question. The first, perhaps, is why does someone actually pay for me to do this? Why are governments funding this kind of work? And in fact, that's really the wrong kind of question, because it's not governments that fund research. It's the wider community, the public. But of course, we should really ban the term of the use of the public, because we are the public. So the question is, as a community of people who pay taxes, whether that's directly or indirectly, why do we think science, research, me getting to do cool stuff in the lab is something that's worth paying for? And the answers to that are a number of things. People are very keen on seeing medical advances, cures. Prestige is a big issue. This is a close-up of a Nobel Prize medal. Countries are actually very keen to get Nobel Prizes. GDP of a small country can be significantly increased by the winning of a Nobel Prize, surprisingly enough. And we shouldn't forget just the idea of just the pure excitement, the idea that we can talk about exciting stuff like galaxies, like the origin of the universe, like how our biology actually works. And that is something that appeals to us. It appeals also to the community, and it particularly appeals to children who may be the next generation of scientists. So there are a lot of reasons why, as a community, we fund research. Why do I do it? Why do I put myself through the rigmarole of running around a place doing all of these things? Well, some simple answers. I have a mortgage to pay. I need a job the same as anyone else. Many people have said that I'm far too curious for my own good, that I stick my nose in places where it's not really wanted and probably not really advisable to put it. And of course, it can be fun. And again, as a researcher, often stuck in meetings or stuck in dealing with stuff that I don't really want to know about, it's worth thinking back to when this was just sort of an amazing thing to look at and just really cool. I do get to do these things. I do get to come out and listen to the rest of today's speakers, which is just going to be really great fun. And that really comes to the core of a point, that as a scientist, this is a privilege. I have an immensely privileged life. I get a good salary to do stuff that I find interesting. it's certainly not a right. And so the question we'd ask is, how do I deliver the best on the public investment in my time? And I'm not going to get into an argument about metrics and how we measure things, because that would be another whole day of talks, and we probably wouldn't agree on the outcome. But that's perhaps not the point. I think the key thing is that this is not a right. As a scientist, I have an obligation to the people who fund me to do useful stuff. And if we can't talk about the details, then we can at least say that when we do this kind of thing, we should be maximising the value, the return on the public investment. And I don't mean the economic return, I mean of the things that I'm generating: papers, results, drugs, media coverage that gets kids into science. These are the things we should be maximising the delivery of for the amount of money that we have available to us, especially in a situation where that amount of money looks like it's going to be taking a bit of a nosedive over the next couple of years. That's easy to say. Less easy to know exactly how to do it. But I think there are some obvious answers. One is simply that we make sure that the science is available for people to build on. I said before, this is a thin veneer. And we need to leverage the ability of as many people as possible to build on it. I mean, I see this basically as a no-brainer. We need to make sure that the widest community possible has access to the results so they can build on them. And we can talk about how best to do that, and several of the speakers later in the day will talk about how best to do that. So I'm not really going to talk about open access to the formal published literature, because sometimes, and I would argue often, formal publication, this process that we go through of traditional peer review prior to publication, formatting, is really overkill. You do not need a sledgehammer to take down a snowman, though sometimes it's fun. Particularly as we had the amount of snow we've had in the UK recently has been really a little bit difficult to cope with. But again, that's a slightly different story. Let me give you a quick example of that. If you'd done a Google search for solubility of Boc glycine in THF at 9 a.m. on the 4th of September 2008, you would have got some not very useful Google results, none of which really had the answer in them. Which is a little disappointing, because the day before that, Jean-Claude and I had actually been in the lab doing an experiment measuring the solubility of Boc glycine in THF. It doesn't matter what that is. What matters is we did an experiment, we got a number out. But this was not available to the rest of the world, except when I did that search, I know that Jean-Claude was sitting in his hotel room actually writing up the experiment and putting it online. I'm not going to talk about the details of this because Jean-Claude can do this much better than I can. The point is, when I did that same search the same evening, the answer is up there. We haven't been through peer review. We haven't gone through a process of waiting 9 months to put a number in the public domain. It's just there. It's available. Now, I don't know whether the following morning some chemical student somewhere in the world benefited from the fact that this number was suddenly available and it made it easier for them to do their experiment. But I do know that there was nothing gained by holding on to it for 9 months. The point is, the web makes publishing, in the sense of making public, extremely easy. And there are a lot of services, systems available for putting a wide variety of data, documents and media on the web. And again, Tony will talk, where's the ChemSpider one gone? Tony will no doubt be talking about one example of that later in the day. We can put this stuff on the web. We can put our lab notebook on the web, inspired again by the work of Jean-Claude. This is my lab notebook. It is on the web. You can go and look at it. It goes up. It's available. The data's there. It's indexed by search engines. You might ask the question, actually, anyone looking at this, can they actually understand it? And that really raises an important question. So perhaps it's better to say of the web that broadcasting is easy, putting material out so that people can look for it is easy. Actually sharing it effectively is a much harder problem. both because you have to make the choice to put that sign on your table, and because you have to make the choice and put in the work to put it in a form that other people can actually find and use. So I would argue, many others have argued, John Wilbank's perhaps key amongst them, that the really important thing to focus on in all of this is interoperability. It's making sure that I don't have to bring that ruddy adapter plug which sparks every time I put it into an American socket whenever I come to the US. And certainly you don't end up in this situation, which you do in various places in Europe where the poles are fine but the size of the plug is wrong. We need technical interoperability, and then we can talk about formats and vocabularies, and there are other people who are much better equipped to talk about than I am, and that requires work. We need legal interoperability. We need the ability to be able to be sure that we're allowed to use data, to use ideas, to use images for the purposes, the repurposing that we want to do that for. And again, Creative Commons and Science Commons have done an awful lot of work on this, and fundamental conclusions that we come to in most cases is that we need to use very liberal licenses to make this work properly. That tends to involve putting things in the public domain and putting them under Creative Commons attribution licenses. And as Lee has alluded to, one of the things that's really proud to be able to talk about today is the idea of trying to come up with principles, approaches, tick lists that make it possible for people to be sure they're sharing data effectively. So the Pantone principles that were published yesterday, which, like all good things that come out of English academia, involved Peter, myself, and Rufus Pollock going to the pub and having an argument. And where this came out of, so for those of you who don't know, Rufus Pollock is one of the founders of the Open Knowledge Foundation. The Open Knowledge Foundation is an important organisation promoting open culture, open science, and open source software. And they have a slightly different perspective on the type of licenses that should be used than Science Commons do. And what was really important about this was that rather than trying to come up with a broad and overarching legal principle about what to do, what we did was focus on what we could agree on and what we thought other people might be able to agree on. So the idea here is that fundamentally, if you want to publish data, to publish science in a way which is actually useful to other people, in a way in which they can reuse it, you need to be able to go through a series of almost tick lists to be able to do that. So this is not a statement about when you should publish or if you should publish. It only applies to when you've decided to publish some data. So if you want to sell data, you want to do that in a proprietary way, this doesn't apply, and we're not trying to cover this. I would say you're making a commercially silly decision if you do that, but that's for me to say. What we're talking about here is when you decide to publish data, please do these 4 things. Be clear. Make a clear statement about what you want to do. Make that absolutely explicit about what you want people to do, and if there are things you don't want people to do. And the best way to do that is to use a legal instrument that actually applies to the stuff you're doing. So if you're producing data, please do not put a Creative Commons attribution license on it, because it's almost entirely useless. Use something that works. I should say these are the shortened versions, the sort of headline versions of sort of 3 points. Do not use non-commercial terms. And we can have a discussion about why that is, but effectively using non-commercial terms obviously blocks commercial use of data, but it blocks the use of this data to make money and return money back to the process of making more data, and that's key. But this is really the absolutely key point. This is the point that we agree. If you publish data, if you decide to publish data, place it explicitly in the public domain, particularly when it comes from public science. And this is really the key. And there are instruments, legal instruments for doing this. So I'd encourage you to go to the website, look at the whole thing in its whole. If you agree, then I would also encourage you to sign up. If you disagree, if you think there are issues with what we've said, please take part in the conversation. This was a real attempt to find common ground and find the things that we can talk about And there are going to be other issues about when to publish, how to publish, what sort of policy conditions there should be on that. And Peter will talk a little bit more about this later. So I've talked about technical interoperability very briefly. I've talked about legal interoperability, but I would argue that these are actually subsets of the whole thing. We need processes, and we need process that actually allows these things to interoperate. All of this governs about 4 things and tick boxes and all of that. That should all be taken away from the scientists. They should just have to make the choice. Do I want to make this open? Yes, no, and have it all taken care of them. Because they're busy people. Tell you that for nothing. So we need systems that actually work with the existing processes that scientists actually are using. And we need systems that work with the people. I've said in the past, if you're using the user as your API, then something's gone horribly wrong. So presenting the scientist with a tool like this is not incredibly helpful. And this is, to be fair, what a lot of the stuff out there actually looks like, when what they're really looking for is something like this. Something straightforward, something simple, where it knows who they are and they know what they're doing. I just want to get on and do my experiment. That's the key thing. Tick the box, move on. And I would argue that what we need to do is we need to capture the objects, the things that happen as part of the research process, and then add the structure on later. And provide the tools that help people to add that structure on. And what I mean by that is to map the processes that I use in the laboratory at the computer when I'm doing things onto agreed vocabularies, onto these interoperability things, but map them, don't insist that I use them when I'm doing the work, when I'm doing the stuff that I do, about which I hope I'm the expert. Map these processes onto those vocabularies when we tell the story, when we have a narrative that we want to fit this into. It's a real problem with a lot of these systems. They make the assumption that I know why I'm doing the experiment. And I can tell you, most of the time I don't. Most of the time I don't know what the data is going to be used for. That's the whole point of making it available, so someone can do something totally unexpected with it. Machines do structure, computational systems do structure, and they need structure, and we need the machines. The scale of the data that Lee has mentioned, that Stephen will talk about later in the day, are such that you cannot handle this with a pen and paper. We need the machines to be able to do anything useful with this. But we don't do structure, we tell stories. So we need tools that capture the pieces of the research record, the samples, the data, the little scraps of text that you wrote down on a piece of paper in the lab. And tools that help us structure that and pull those down into a story when we write a paper, when we write a report, when we're doing a presentation. And tools that actually are aware of the structure that's already there. They're capturing and leveraging the structure that's already there as part of the process. So Lee has mentioned the work of Microsoft in this space. Peter will talk later about systems that do this in other places. I wanted to show an example of some fairly preliminary work that I've been doing. I know I shouldn't possibly be showing Google products in a Microsoft space, but that's what I work with because I'm too dumb to work in C#, basically. And so the point here is that I'm taking a notebook. I'm writing something about an experiment that I am doing, just typing it in. But what I'm doing is bringing in information from other places. These are just RSS feeds. So this robot, this system, is just grabbing information from this feed and it's using it to populate a drop-down menu. So as I go along and I want to talk about what I'm doing, talk about the inputs, the ideas that led to this experiment, I can just select them, insert them, and the system creates the link. The system puts that information in. And then my tweets come up. Again, if I'm referring to the literature, I might have some literature online, and again, I can just create the link. Ideally, if I've generated some data, or if I'm going to generate some data, that already is available somewhere online. Maybe it's secure, maybe it's fully available. But again, it's being dumped somewhere without my intervention. And again, there's an RSS feed So this is a beta product, obviously. And in fact, this is about to crash. But data, and an image could be data, can be inserted automatically into the process. Again, this is a fairly crude example, but all I'm doing is typing away and inserting objects that are inputs, inserting objects that are outputs. And so the question is, how do I then get the structured data out? I want the system to have captured what's happened. And so this has been automatically generated. This document, this thing which has an identity on the web, has inputs and it has outputs. And I've captured that information. Something's coming in, something's going out. Of course, if we're doing it semantic web, then we should be generating that in semantic webby stuff. And I've generated this RDF automatically. Now, I've faked this, actually. The namespaces don't exist. I haven't put these up online. But the point is, this is a snippet of RDF generated automatically from my typed record of an experiment and selecting a couple of things from a drop-down menu. It knows who I am. It knows who the authors of the document are, and it put those in automatically. It knows what the inputs were, and it knows what the outputs are. And those can be more sophisticated vocabulary terms, which I might have selected from a drop-down menu. But we can capture what I was doing as I was doing it and automatically create a structured record which is then available for machines to do things with. So what can we do if we're talking about open science? Well, I'd say we're actually technically able to share, and I would say, going out on a limb, we're actually, if we made the choice, we could choose to share the entire research record. We need to do a lot of building, we need to do quite a lot of work, and it would cost a bit of money. But we could do this today, if we chose to do it. The question is whether we choose to do it. As a community, both a community of researchers, specific communities of scientists, and as a community that pays for this research either directly through taxation or indirectly through products. Those are the choices we can make, and the answer that you fairly resoundingly get back at the moment is that people do not want to do this. The mainstream response that I usually get giving this talk at a fairly conventional conference looks something like this. In fact, slightly more commonly it looks something like this. The pram has definitely, the rattle has definitely been thrown out of the pram at this point, which leads to a lot of these kind of conversations. And I leave it as an exercise to the reader as to which one of these is the scientist, which one of these is the funder or the member of the public, or indeed the institutional repository operator. So the question becomes, how do we actually persuade? How do we, if we can make a case, and I believe we can make a case, that we can do science more efficiently, we can do research more effectively, we can make stuff more available, and that would be a good thing. How do we persuade community to do that? And to be honest, I'm actually not at all worried about this. And the reason I'm not worried is because of graphs like this. This is the reflexive, lazy example that everyone gives of the data deluge problem, but it's a fairly apposite one, and it's got some interesting, more recent wrinkles on it. So these are submissions of DNA sequences to GenBank over the past 20 or so years. This is essentially exponential. The sharp-eyed amongst you will note that as it gets towards the last couple of years, it's no longer exponential. The reason for that is that 99.9% of the DNA sequence data generated in the last 2 years has not been put into GenBank because it can't cope. This is a scale problem, and you could draw this graph for protein structures, you could draw it for astronomical data, you could draw it for chemical reactions, you could draw it for just about anything. Everything is scaling exponentially. And we're generating more data from the exponentially greater set of experiments that we're doing. And this creates a problem because of this graph. We're not getting smarter or faster. The computers may be, but we're not. Which leaves us in a situation like this, where the average scientist, the person actually doing the research on the ground, is running faster and faster and faster in a fairly futile attempt to just catch up. The point is that the human scientist, the person who remains at the centre of a scientific research effort, at least for the moment, singularity is not upon us quite yet, just doesn't scale. The only thing that really scales effectively in our technological world is the web. Governments do not scale. Policy generation from the top down does not scale. see under various current UK government acts, not to mention Australian government acts. Research groups don't scale either. You take the average research output of a research group of 50 people, it ain't even 10 times the average research output of a group of 5 people. And network theory tells us there should be an exponent in there. It should be more than linear. Research groups do not effectively scale. You do not get more research out by just having bigger research groups. You do not get more research out by simply concentrating effort in a small number of places. The web scales by distribution. The web scales by exploiting network effects, which means that just to survive, just to be able to keep up, the scientist is going to have to be web native, which means connected, which means wiring yourself into a network that provides network effects and doing that effectively and doing it in a way that creates outputs. And that means sharing. This is not a new concept. It goes back perhaps most eloquently to Merton in the 60s and 70s and 80s, but equally it goes back to Bacon, it goes back to the beginning of the Royal Society, where sending letters to each other as a way of describing the latest findings wasn't scaling. So what did they do? They created the journal. The scientific journal, Philosophical Transactions of the Royal Society, was the web of the 18th century. And it's not done a bad job for the last 300 years. It's just not cut out to deal with it anymore. You have your effect in science. Going back to that slide with all the names on it, you have your effect by letting other people build on your work. If you don't do that, you're not having an effect. And we're used to these networks in research. We're used to this concept of the journal, of networks of papers, which may be the odd bit of data connected up at some level. But this network isn't just papers if we're going to be trying to do this effectively. It's the images, the ideas, the thoughts, the presentations, the lab notebooks. All of these things build a network that, if we can build it effectively, will give us the network effects which will let us do science more effectively. And you can choose whether or not to make these things available, but if you choose not to make these things available on the network, then you're not connected. If you're not connected, you don't exist. It doesn't matter how good this idea is if no one knows about it. When was the last time any of you actually cracked open a paper, leather-bound version of an encyclopedia? And how many of you haven't done a web search in the last 24 hours? Where are people going for information? So it's open content that builds this network, that will allow us to build it, that will allow us to make it interoperable and make it effective. The network is the only way that scientists are going to be able to keep up and to be able to function effectively in 21st century science, in 21st century research more generally. If we build these tools that help researchers to manage and build these networks, then I think the rest of it just follows from pure competitive interactions. People want to be at the top of the game. They're going to have to do this to be at the top of the game. So I need to thank a number of people for contributions to this talk, specifically in terms of images and inspiration for how I've given it. Thank you for coming, and I'm happy to answer any questions.
About 5 minutes for questions, if any.
Yep.
How do we filter out the garbage? I mean, not all data is created equal.
No, certainly not all data is created equal. Yeah, sorry. So the question was, how do we filter out the garbage? And this is a general problem. It's not restricted to research by any means. There's an awful lot of garbage out there. The bottom line, at least at the moment, is that web search tools do a pretty good job at some level of finding stuff that's well connected, finding stuff that other people are referring to. And that is why you need to have the actual objects exposed on the web, because if people don't link to them in the way that we don't at the moment for research, those kind of PageRank style mechanisms do not work. That's level one. If we cite the research objects properly, then Google will do some of the job for us. The second level is building better social networks that then start to help us filtering. So these networks of data and of objects and thoughts are equally networks of people. And so I don't know whether anyone's actually going to mention this today, but there are tools available that help people filter other people's content. The one that I know a number of us are very fond of is a tool called FriendFeed, where I can bring a bunch of content in, and that's fine. I'm saying this might be of interest to people, but what matters is whether other people interact with that content, make comments on it, these kind of things, and that pushes those objects up to the top of the pile. So there are the beginnings of an idea of how we can effectively socially filter content as well. And then there are all the questions of, okay, do you just end up with an echo chamber? Do you just end up with self-reinforcement? And that's, again, why I put up a number of the people on that first slide are people I violently disagree with, because they challenge you to rethink, the reflexive, easy state. So filtering is not an easy problem to solve, but you can't build a filter without having the stuff there that you want to filter first to test it against. Yep.
Are there search engines that generate a web of results as opposed to a list?
The question was, are there search engines that generate a web of results rather than a list? That's a really interesting question. I've never heard that question asked quite that way before. Not at the top, not at the top level in terms of, in a sense, all search engines do because they provide you with hyperlinks, and those hyperlinks are... and I have seen some quite clever visualizations of search results. The major problem with that being that Google doesn't let you actually have an API onto the search results. I'm not sure whether Bing does or not. But either way, because those are very proprietary outputs, it's difficult. It's a classic example of the genre. It's difficult to build the tool over the data because you're not legally sure what you're allowed to do with the data. I'm sure there are people working on those kind of things. I know there are people working on search visualization very, very hard. But I couldn't give you an explicit example of it. Bill?
One example that does spring to mind is biomed experts. If you do a co-author search, that graph that comes up, it's JavaScript, it's really very useful when you're trying, for instance, to figure out who should review this paper if you're an editor. You can use that graph to find out if the suggested reviewers have published with this person. You can see clusters of authors and try to pick one from each cluster so you've got a good representation of the field in your referees. It's really very useful. That's the best one I've seen.
And what is it again?
It's called Biomed.
So it's Biomed Experts, which is is it a product of Thomson? I can never quite remember. As a separate company.
I have no idea.
It uses the underlying data of the co-citation network to it basically generates a co-authorship network of scientific authors based on published literature. And one of the main things it displays is you look for a person, and then it displays a network of co-authorships with that person. So essentially, it's kind of what you were asking about, but for a person rather than for the research objects, which is kind of the wrong way around. Because if you take Jeff Jonas's and John Udell's soundbite seriously, data finds data, then people find people. It's kind of the wrong way around for research, but it's a start in the right direction. Sometimes you just want people, that's true.
All right.
Okay.
All right. Thank you very much, Cameron.
I think it's back into that.
Yep. Where were you in here?
Already.
Oh, was it open? All right, everyone. What I'd like to do now is hand the floor to Jean-Claude Bradley to talk to us about open notebook science.
Thank you. So thanks very much for the invitation. Thanks to Hope and Lisa. You guys did a great job in setting this up. What I'd like to do is to follow up on what Cameron was discussing in terms of why it is that we need openness. And I'd like to take a pretty concrete example of that and show you in a chemistry application what kind of openness currently exists and what's actually possible. Okay, so I'm going to be talking about open notebook science with free hosted tools. And these are the issues that I'd like to make a case for open notebook science. The concept is very simple, at least in chemistry. If you're doing chemistry experimentally, you have a lab notebook. That lab notebook is typically an extremely private document, something that nobody else will see, something that no one will read probably when you leave the lab. And there's a lot of information in there. And the question is, what if we make that notebook publicly available? Does that help? So I'm going to try to make a case that it does on these various levels. So first of all, if our current system is working very well, then what's the motivation for doing this? And I'll show you a few examples of where the system really isn't working very well in chemistry. Is open notebook science difficult to implement? I'll show you that there's at least one way of doing it that's free and fairly simple to do. Does it prevent peer-reviewed publication? No. I'll show you an example, although that will be qualified, which I'll go through shortly. Can you discover the data? As Cameron was saying, if you put it out there and people don't find it, it's not very useful. So there are ways of putting the data out there that people can find it, even if they don't already know about your project, and that's really important. Can the information be easily archived and cited? So I'll show you some very recent work of where I think we have a pretty good system for archiving. And citation, we've been able to cite our lab notebook pages, and that's worked out. And finally, is ONS compatible with IP protection? So I'll mainly no, but there's a small exception to that you might find interesting. So how bad is our current system? Well, I'm picking an example here as a chemist that I think most of you can relate to. If you're familiar with the concept of solubility, how much sugar goes into coffee, you can only put so much. So there's a certain amount that you can put in. And it's such a simple measurement that you'd think it'd be very easy to find, right? So EGCG is actually the antioxidant in green tea. Okay, so it's a compound of tremendous interest. There are lots of researchers that are doing things with it. So if you wanted to start to work with this material, you probably want to find its solubility to see what kind of solutions you could make. So if you use our current scholarly communications, you go to the peer-reviewed literature, you go on Ballstein or use CAST to find information, you'll find this paper that says the solubility is 521.7 grams per liter. That's actually an enormous amount. The number itself really doesn't make sense. And what's really interesting is that this actually went through peer review. So the people who reviewed this paper didn't think that was a problem. But luckily, there's a citation. Okay, so if you take the first paper and get down to the citation, you'll see that actually it was a misprint. In the original article, it was 5 grams per liter. And the solubility of caffeine, 21.7, was accidentally put at the end of the number 5. Now the issue here is, okay, I have the number 5. Now where did this come from? Unfortunately, could not find a reference for this number. Okay, so we'll keep searching. If we go to Sigma Aldrich, it's a very popular source of chemicals, and it also has a very good reputation for having good data. So if you want to know the density of a compound, or if you want to know some kind of practical property, it's usually pretty good. So for this particular compound, it says that you can make a solution at 5 milligrams per mil, which is 5 grams per liter. It doesn't actually say that's the solubility of the material. It doesn't say it's the maximum solubility. It just says you can make a solution of that number. Okay, so maybe that's where the number came from and it got misinterpreted. So we keep doing more search in the peer-reviewed literature, and we find another paper that said that the maximum solubility is 2.3 grams per liter. So this is actually troubling as a chemist because I have two really strong, what are typically going to be good data sources. I have a peer-reviewed paper, and I have, from a company catalog, a company that I trust very much. So how do we make sense of this? Well, for the company catalog, you're completely out of luck because there's no information about how the number was obtained at all. There's no reference. It's just a number, and if it's a typo, you have no idea. Now, we get a little bit further with that last paper because they do have an experimental section where they describe, how they actually did the experiment. And this is the best that you can do in chemistry right now in terms of finding out how a researcher actually carried out their experiment. But this is not the lab notebook. Okay, this contains summarized information. It contains a level of abstraction that, it's a little bit more complicated what actually happened when they tried to do it. For example, here they say they sonicated this, but they don't say the power. and then they diluted and filtered. They don't really say how they filtered it. So I can see some issues with this, why the number might not match the company catalog, but I don't have enough information to be able to assess which number is more likely to be correct. So the reality is, if I want to know the solubility of this thing, it's probably easier for me to do it, because the literature isn't helping me as much. Okay, here's a second example where we actually will show some notebook information being produced. The sodium hydride oxidation controversy. How many of you have heard about this? Some of the few people related to chemistry here. This is actually a really interesting story. You don't really need to understand chemistry to understand how important this is, but this is something that most chemists would think is impossible to achieve. And it was published in a highly prestigious journal. And so it did generate a lot of controversy. Okay, so this was a paper that claimed to do something that most chemists would say is impossible. Now, the way that I found out about it was through the blogosphere. As Cameron mentioned, FriendFeed, it's an aggregator that I prefer to use as well. It's very, very efficient. And you see people that basically just start to make comments about this. And then something really interesting happened. People actually started to try to reproduce the experiments, but they also provided the raw data so that people could evaluate whether or not what they were saying, was consistent. So the Totally Synthetic blog tried to repeat one of the experiments and got a 15% yield. But again, very importantly, they published the NMR on their blog. So this information is critical for being able to ascertain whether or not that 15% is a typo. If you're a chemist, you can go in and you can actually see that 15% from the plot. So that's kind of interesting. Now, the 15% was much, much lower than what the researchers published originally. So there is still a conversion, but why is it so different? So I was talking to my own students about it, and we were thinking about trying to repeat this. And so again, this is a experimental section in a chemistry journal, peer-reviewed chemistry journal. It does have information, but it doesn't have the lab notebook information. So these are some pretty general terms. I don't know how they monitored the reaction. I don't know exactly what they did. I have a rough idea, of course, but I can't try to reproduce what they did and then see as I'm going through if everything is matching up. So the best we can do is just, try to take a shot at this. So my grad student, Khalid, and my undergrad, Marshall Moritz, basically just tried to repeat this. And we also posted the raw NMR data directly. And in this case, it was on a blog post, but it was also on a wiki, as I'll show you shortly. And we found actually a 0% conversion. Okay, so we're getting really wildly divergent results here. And again, the blogosphere comes to the rescue. Someone found a paper from 1965 where this effect had actually been previously reported. And it turns out that it's due to the particular material, sodium hydride, can form something at its surface, can form a layer at its surface that completely changes its chemistry. And so this is actually really useful information because this reagent is used by a lot of chemists. And even if you're not trying to repeat this, you want to look out for possible side reactions. So this is great, and this all got sorted out. But the final result, if you go back to the journal where this was published, all you find is that the paper was retracted and there's no reason given. So all of this information, all the knowledge that was gained by sharing all the information, it's still there, all right, and you'll find it very easily. Just do a Google search. Search for sodium hydride oxidation. You'll find our experiment at the top, the second one as the explanation, and then the third one as the second open notebook attempt. So, and this is really what Cameron was talking about, that the information can be found, and this is how people are likely to look for it if they want to learn more about this. So it's interesting to see the publishers stand on this. There's a lot of useful information, but it's not being shared. So a third example that I think is particularly fascinating is Alexander Graham Bell's notebook. This is a recent book. Seth Schulman basically was interested in the notebook, wanted to see when the telephone was invented in Bell's notebook. So he actually looked at it and didn't find the invention before the submission of the patent. And he ended up writing a book about the whole sordid affair, that it's likely that Bell actually stole the telephone directly from the patent office by visiting it on that day from Elisha Gray. And the fact that he did it for love is a very interesting twist to the story. So I would strongly recommend this. And it basically shows how just providing the lab notebook, which, by the way, wasn't available to the public until, I think, 1990, which is why really people hadn't looked at it in detail. And now you can find it on the web. I think since 1999, it was just put on the web for free. So again, something immense that we all thought we knew about isn't quite what it seemed. Okay, so what I'm talking about is open notebook science. And if you want to see more examples or you want to see articles that are written about this, if you go to Wikipedia, that's a pretty good place to start. So what I've been talking about so far is open notebook science in the sense that we make all of our information available immediately. Okay, and that's how I'll be talking about it in this way. But it turns out that you might not quite want to expose your work in that way. So we've developed these logos, Andy Lang and Shirley Wu, to sort of explicitly express what it is that people can expect when they're looking at your notebook. So the top one is what I've been discussing, all content immediate. And Peter, we were discussing before the talk that you could have all content but delayed either because of a publication you're waiting on or possibly an intellectual property issue. So there are different ways of doing it, but I think it's important to be explicit about what you're doing. Because if you're doing the top one, what it means is that people are looking at your notebook, and if they don't find something, they can assume that you haven't done it. And then they can go and possibly do it or make decisions based on that. So it is important to be clear about what you're doing. Okay, so this is really sort of a philosophy. The question was brought up earlier about, well, how can you trust data? Data is not all created equally. And I think that's a big problem, is the way in which it is presented, right? We try to tell our students that there are certain things as facts, but there really aren't. There are certain things like the melting point of water or the boiling point of water that have been measured so many times by so many people that you can use it as a fact. But the reality is probably most of the measurements in science and certainly chemistry may have only been measured once or twice. And I just show you an example of how hard it is to actually evaluate those data points. Okay, so what we want to do here with Open Notebook Science is maintain the integrity of the data provenance by making all the assumptions explicit so each person can evaluate the source of the information as they wish. So we're moving away from an environment of trust to one of proof. Okay, so the question is, if you see two data points, it shouldn't really matter where it came from, whether it came from the most prestigious journal or whether you found it on Google and have no idea who the person is. If you can see the evidence that they're providing, that's all you need to be able to assess that particular data point. Okay, so I want to go through a very specific example. So this talk is about using free and hosted tools to do this kind of stuff. So I'll be showing you exactly what kind of tools. Here's a table. Okay, again, I don't want to focus too much on the chemistry, but just to note that as a chemist, you see that there's a trend there, and there's one number that's totally out of whack. So if you were to see this in a traditional paper, there's not much that you could really do about it. Because is the number a typo? Is the number really something that's deviant? And you have no way of drilling down usually and actually finding out where that comes from. So in an open notebook, what you do, and then we use a wiki, we use Wikispaces, which is a very nice free hosted service. We can record the log of what the students actually did. So we can investigate here at exactly this time point that the samples are vortex, but the exact amount of time was not recorded. Remember I was talking about assumptions being explicit? Often it's very useful to know what you don't know. And so in this case, the students didn't measure it, and it turns out that's actually important. So how are you going to find out? Well, you're going to redo this experiment, but now you're going to record this. And that's really how science can, get much better as you keep going through these iterations. Okay, so you can make all kinds of things available. You can also make the rationale of the findings explicit. So you can make a statement, but then you can link to various pieces of the puzzle, various parts of raw data that support your statement, which doesn't mean that everyone will agree with you, but that's okay as long as they can debate the raw data. So there's all kinds of raw data these days. We've used images. We've used short videos that we upload on YouTube. This actually is a very convenient way. Take a 15-second YouTube video of an experimental setup, and it saves the student from having to write a long paragraph about how they did things. But more importantly, the video doesn't hide things that the students would forget to write, like where the thermometer was or exactly what was going on. So it's actually a very efficient way of doing it. Now, we make very extensive use of Google spreadsheets, and so we're reporting solubilities in this case. We have numbers, but in a Google spreadsheet, these are not just numbers. If you click on these cells, you'll actually see the formula that are used to calculate all these numbers. And oftentimes, when a number doesn't make sense, if you go back to the Google spreadsheet, you'll find that the student made a mistake in the calculation. And that's why it's important to, not just have the numbers, but be able to track how the numbers were converted. Google spreadsheets are sort of like a wiki in the sense that they have different versions. So you can go down, and if you want to see if an error is corrected or if a student made a change of any kind, you can pretty easily just go back to a previous version. The wiki, where we actually write our experiments, is exactly the same way. You can hit the revision history, and you can see who made the change and exactly what was the change by comparing two versions. So as a specific implementation, I really like wiki spaces because when you compare two versions, the new text is in green and the stuff that was deleted is in red. So I interact with my students a lot this way. As soon as I see them recording something about the experiment they did, I'll go in and I will make comments in bold usually, and then they can respond to it. So it's a way of interacting very, very quickly with students that are in the lab. Because typically experiments are pretty complicated to make sure you have all the information, you analyze it correctly. So I really like a wiki for that. Now, another pet peeve of mine in traditional publication of chemistry, these NMR spectra that I've been talking about, these are normally stored as PDFs. So even in the supplementary material, when you download them, it's really just an image, and you can't blow this up, okay, because the information is not there. But it turns out that when you blow up these peaks, there's a lot of useful information in the impurities. There's a lot of useful information that is just simply totally absent when you convert it into a PDF. So we use this open format called JCampDX, and we used this open source JSpecView that was developed by Robert Lancashire, and this enables us on a web interface. So people come in with a browser, they don't have to know that all of this is running. They just take their mouse, expand peaks, and they can interact with the data in a way that's much more useful. So we try to leverage as much as possible what's out there. Tony is here. He'll be talking about ChemSpider. And ChemSpider is just a way of keeping track of molecules, manipulating them, searching them, and we can also upload our data directly to ChemSpider as well. Okay, so like I said, we can upload spectra. Now the interesting thing about this is that when you try to upload a spectrum on ChemSpider, it asks you whether or not you want it to be open. And if you make it open, there's a lot of interesting consequences from that. One of the consequences that we didn't foresee at the time was if it's open, we can use all the spectra to turn into a game, for example. So Andy Lang, Tony Williams, Robert Lancashire, we all came together, collaborated on this project, and we now have a game that uses every NMR spectrum uploaded on ChemSpider that's marked as open data, automatically goes into this game. Okay. So I want to go through more of these items that I was going through. This is an example of a chemical reaction that we do where we mix components together and sometimes we get a precipitate. So what we want to do is to try to understand if we can predict when this is going to happen. Okay, so that's the connection to the solubility data that I was talking about. And what we decided to do is to try this interesting approach of using crowdsourcing for anyone in the world to come in and contribute a solubility measurement in a non-aqueous solvent, so any solvent that's not water. We got some funding from SubMeta. They funded 10 $500 awards. We got some chemicals donated by Sigma Aldrich. Nature contributed some magazine subscriptions to the winners. And the concept was very simple. Just submit your measurements, put them in an open notebook, and we will basically judge them. We've just completed the first one where all the awards were made. So these are all students, either graduate or undergrads. And I think it was a very good experience for them. We have 6 judges, many of whom are actually in the room here. Bill is here. Tony, Cameron are here. And basically, these judges would interact with the students on the wiki, just as I was mentioning. They would make a comment, and then the students would respond or not. We didn't award the prize to the student who made the most measurements. We awarded the prizes to the students who were the most responsible scientists, who actually interacted and responded in a way. And so I'm very happy with the way that was designed because it wasn't just number crunching. Okay, and we had other teachers actually use this in their own labs, which is kind of an interesting approach in a teaching lab to try to get students to contribute to science. Now, I talked to you about searching. So, all right, this is how we put the stuff up there. That's all great, but how are you going to find it? Well, if you're part of the project, you know, this is a common way of finding it. This is sort of a table of contents that has all the experiment numbers and a brief description and who did it. So if you already know about it, this is probably not a bad way to do it. But that's not how most people are going to find the information, obviously, right? Because they don't know about it. So what we do is we have another Google spreadsheet that aggregates all of the results from all the experiments. So over that year, we have, I think, like 700 different measurements, and they're all in a Google spreadsheet. And the nice thing about this is there's a nice API that enables you to query the Google spreadsheet like a real database. And we can do things like this. So people like Rajarshi Guha can come in and collaborate because the project's open, right? They can find it, they can collaborate with us and make their work open. And then we can, you know, have drop downs, for example, where you're going to search for vanillin, any solvent. And then it gives you a little table showing you all the different measurements. And you can click on these and actually end up, you know, looking at the actual lab notebook pages. Okay, so how can the scientific process become more automated? One of the longer term benefits that I can see, and certainly Cameron has sort of, you know, has introduced this concept earlier, is that, you know, it's very important for machines to be able to understand the information just as much as humans. And we're kind of in a very interesting time right now where if we make the information, you know, in some format readable by both humans and machines, they can start to collaborate with each other. And so one of the things that what we're trying to do is to basically have bots interact with our data and make a useful contribution. So a quick example of this is we're talking about these NMR spectra. So normally a chemist would manually read them and make the calculations. But we've actually have code that automatically goes to from the Google spreadsheet as a web service and integrates it and then does the calculation and returns the final value right here. This is the final solubility value. So this has been very helpful because the students, you know, will make mistakes. That's always going to happen. It's just a question of how easy it is to find those mistakes. And if you have bots that go in and can, you know, take up a lot of the drudgery, a lot of the things where it's very easy to make mistakes, you know, they can contribute, and the humans can contribute what they do very well. So I see if you go through this, see how the information is represented, the APIs that we have, we really want to move towards more and more automation. Okay. So the last part of this in terms of what we're going to do with the data is we've started to build models. So if you're looking for a solubility measurement, it might have been measured, but if it hasn't been measured, we're trying to come up with ways of predicting the number for you. So if you want to do a reaction and it hasn't been done, maybe you can take a guess at what a good solvent might be. So that's something that we're currently working on. Now, one of the criticisms of this project often is that, you know, we're just empirically collecting numbers and putting them together. But actually, there's some good science that we've discovered from this as well. Because we're using this NMR method, we can actually see all of the chemicals that are being produced, if at all, during the making of the solution. And what we found by accident is that for some compounds like this, in alcoholic solvents like methanol, they actually form what's called a hemiacetal very quickly. And in this case, if you go back to this solubility of this compound was actually reported in 1982, and they did not find actually that there was a chemical reaction between the solvent and the solute. And, you know, maybe the information was in here, but the amount of detail isn't provided that we can't go back and see that they missed it or that the method they used, you know, wasn't going to detect it anyway. So this is kind of interesting, and it turns out this is pretty general for a whole class of compounds. So solubilities that have been reported in the past are not really solubilities, they're actually reactions. Okay, so finding the data. I showed you the Google spreadsheet. We store everything. Again, if you don't know that spreadsheet exists, how are you likely to find it? We get about 100 queries a day on specific solubility requests, and most of them come from a Google search or a Wikipedia search. On Wikipedia, if you look up the molecules that we've done, you'll see there's this ChemInfo box, and we have the reported solubilities, and then there's a link. you'll notice that none of the other properties typically have links in Wikipedia. So what we're trying to do, again, is to bring that concept of proof as opposed to trust. Okay, so if you want to find out where these came from, click on that link. It takes you to a table, right, of all the different solvents. Clicking on one of these shows you the individual measurements. So different experiments provided different numbers for that same solute and solvent. You can then drill down again, click on one of these. It takes you to the lab notebook page. And then you click through to the associated Google spreadsheet that has all the calculations and everything. So you want to use the number quickly, that's great. You find there's something wrong with the number, you can go in and try to see what it's based on. Okay, so a couple of more issues. How does this affect publication? Well, because what you're doing is you're making all this available in real time, some publishers, will consider that a preprint, and if their preprint policy is non-existent, then you won't be able to go to that journal. But it turns out that there are enough journals out there that are peer-reviewed and that will accept preprints. So we've gone through and actually not only used the lab notebook for a particular project, but we've actually written the paper on a public wiki, so all the drafts are available as well. And the idea here is that at all times that the world can know exactly what our state of the knowledge of that particular project is. Now this, of course, is a classic preprint. It just happens to be on a wiki, but it's just the paper that's already been made public. And again, I was talking about citation at my very first slide. This is a very convenient thing. If you have your lab notebook that's public, you can actually use a specific page as a citation. Okay, so you'll notice here that the melting point, for example, was taken from experiment 99, whereas the NMR was taken from experiment 203. Normally in a paper you don't see that distinction, but it turns out that these are different batches that were made, and maybe they're not identical. So if you're trying to find out why is your melting point not corresponding, you would have to look at the specific batch of where that compound was made to see if there might be an issue. So we published this in Journal of Visualized Experiments. Okay, and this one actually has a video component as well, but that's sort of besides the point. There's also the actual text that we wrote on the wiki. And another tool that we made use of was Nature Proceedings. So while the paper was under peer review, we submitted it to Nature Proceedings. And this has the advantage that it has a DOI, it has a standard author list, it's archived by Nature. So it is something that actually I found does tend to get cited. And you have nothing to lose if the journal accepts preprints. Now, when the paper comes out, Journal of Visualized Experiments is open access. So we've actually really grown to value this tremendously because you retain the copyright, and that lets you repurpose that exact same copyright for whatever purpose you want. Tony's going to show this a little bit later, but you can take that same paper and through a ChemSpider journal, it'll automatically find the molecules, and when you hover over them, it'll show you the image. Okay, so if we had published in a non-open access journal, we'd have some issues with this, with getting permission to actually repurpose it. And there's opportunities that just keep coming and coming when you retain that copyright. So this same paper was turned into an application note with Method Toledo because we had borrowed their robot to actually do the experiment. So again, you have this way of redundantly distributing your message. Okay, so and here's where a little issue comes up. Okay, because if you're repurposing the same content, you're trying to reach a wider audience, it's going to affect the number of times that each one of those sources is actually looked at. So while I'm a huge fan of article level metrics, I think you have to be careful how you interpret your success or failure based on them. Okay, it's just a number. It gives you some very useful information, but don't put your self-esteem into the number of your any specific article level metric. Okay, so there are other approaches to these open notebooks. Cameron has a system that he showed briefly. It uses a modified log engine. We have Steve Cook is here. His student uses Open Wetware, which is another wiki system. Okay, and so there are other approaches to this. If you're interested in learning more about them, I can certainly discuss them with you. So the final piece of this is what do we do in terms of archiving the material, having a place to cite it, having taking a snapshot. So I think there's a huge opportunity right now with libraries as to how they manage this kind of information. What we've been doing recently is actually coming up with a way of archiving these so that people can actually see what the state of knowledge was. People ask us often why we don't use the Wayback Machine. Basically, it doesn't work very well for our project. I don't know if you ever tried to look at some of your applications on here, but there are actually entries. Okay, they're not taken every month. They're not taken very often. But this is what they look like. So even though Wikispaces is not protected by password, for some reason, when they try to archive it, every page looks like this. So you can't really rely on these default mechanisms often. So you have to sort of take a proactive approach, I think. So with Andrew Lang, we've basically gone through, written some code to address specific kinds of archiving, specific kinds of backups. So we have this ONS preserver, for example, that will go through a Google spreadsheet that has a list of all the items that are high priority that we want to keep backed up. So it'll make a copy whenever this runs. We use a Windows scheduler, just goes in once a day and just executes it. Okay, and luckily Google Spreadsheets have a very nice option that they can be downloaded as Excel. And the reason that's important is that I was telling you about the calculations. I also told you about web services that we're calling. When you store them as Excel, it retains all the calculations, and it actually, even though it captures the number from a web service call, it will give you the link of the web service that it actually used. So again, if you want to track back to see exactly where the information comes from, this is extremely useful. So where we are right now in terms of this whole archiving issue, we have a service that again runs once a day that simply backs up the actual Google spreadsheet that summarizes everything. Then we take periodic snapshots where we actually make copies of all the relevant files and the lab notebook. And then we can actually put them in citable storage. So we have them available from lulu.com, so you can actually buy this CD at cost. It's like $5, and that will have the archive for a particular day. We also published it in a book, and if you're interested in seeing this, it basically takes the Google spreadsheet and it puts them in a human-readable format, so you can browse through the book. And this book corresponds to this data archive. Okay, so this is the concept here. Okay, so basically the way this works, just slightly more technical standpoint, is Wikispaces has a way of exporting the entire wiki as HTML. So we start with that. And then it makes local references to any images or files that were uploaded onto the wiki. And then we have all the spectral files, the NMRs. That's actually a very short manual step. And then Andy has written code that actually goes through and identifies how many Google spreadsheets are cited from each page. And then it downloads them and puts them in a file to have a local reference when you look at the archive. So if you go into this archive, for example, from February 11th, you'll notice that this is all local. And when you click on any of these links, it will just redirect you locally on that archive. So again, this is concept of a snapshot. On this particular day, what did all of the data sources look like? Okay, so this is the way it looks like on Lulu when you publish these. We've also used DSpace at Drexel as a zip archive. Okay, so the main difference is that when you download this, there are certain functions that you can't do, like viewing the interactive spectra. Okay, but otherwise, everything else is basically the same. So we have made use of these, and we have this data book which is available. So this is kind of interesting. They charge a fairly minimal amount to simply print out the book and publish it, and then you simply pay for shipping, and this is what it looks like. Okay, so that's basically it for the archive. Just step through for a minute here in terms of what the initial questions that I asked. Is our current system working? I show you 3 examples where it isn't working the way that the chemist would like it to. Is it difficult or expensive to implement ONS? Not necessarily. I showed you Wikispaces, free and hosted, Google Spreadsheets, completely free and hosted, and the code that we've written for all this archiving, of course, is available to anyone, so it's certainly possible. Does it prevent peer-reviewed publication? No, but you do have to look at the publisher to make sure that they allow it. It is discoverable. Like I said, Google and Wikipedia are our main issues. Can it be easily archived? And this is a very recent thing where I think we're pretty good on archiving right now. But in terms of intellectual property protection, I think this is very problematic. If you intend on patenting anything, you have to understand that this is a disclosure every day, every hour that you make this available. Although Steve Cook actually has a very interesting strategy, because you do retain the ability to file for a U.S. patent a year after you make it public. So even though you don't have international rights, there are still some ways that you can get some intellectual property coverage. But for the work that we're doing, that's not an issue. We're just not going to pursue that. So I'd like to thank you very much for your time.
Are there any questions for Jean-Claude?
Yes.
In the Google spreadsheets, is there any plan to make the smiles or the chemical structure, an actual chemical structure, so that you could search through that way? Or ultimately, do you have to rely on exporting to Excel and use some plug-in to do chemically aware searching?
Yeah, I mean, the idea is you have the API that you can query it in sophisticated ways in terms of, only give me the compounds with this solubility range, or do this substructure search. So yeah, so those do exist, but they don't exist as an inherent property of the Google spreadsheet. That would come through the API, and we have those things written. So that's not an issue. But yeah, we do use Smiles as it's probably the most convenient way to store the information in a spreadsheet like that.
Well, one thing that's happened, that I was doing a search on John Wilbanks, is that he had a column that said the Journal of Visualized Experiments, Joe, started as open access, and then last year it decided arbitrarily on their part, I guess, not to be open access. So is that a problem, where you predicated everything on open notebook, and then suddenly one of your sources says, oh, by the way, it's not going to be, and can you get access to your own data and extract it and then post it yourself somewhere else?
Well, you can do that, but I mean, the other thing is Jove has not, like, everything that was open access is still open access. So our paper is still open access. What they were saying is going forward, yeah, I mean, and you still can make it open access, the gold approach, you can pay for it. So that's still available, but yeah, no, they haven't, done a bait and switch where it was open access, or you thought it was, and then they removed it. No, it still is.
So the whole system you have going is really, really impressive, and how well the open notebook science is working. And I'm curious, if a chemist just like you, who is not doing any of this, wanted to start doing it, how difficult do you think it would be to copy?
So the question is, how can you get involved or start? I went through very quickly, showed you the best of what we've been doing. You certainly don't have to implement every single thing that we have. I have taken a chemist actually through this, and it's just a question of creating the wiki, showing a little bit how to create the Google spreadsheets, how to connect them. There's also a blog component to this where we kind of talk about our progress and then link to the actual notebook pages, because we certainly don't expect people to read the notebook like a magazine. But I mean, in terms of some of the archiving, some of the more sophisticated stuff like that, I don't think you need that initially to get started. I think you just simply need to have the wiki created and learn a little bit about how it works. I like Wikispace's too, is that they have a pretty nice visual editor, so you don't need to really know any wiki text to sort of get going, which I like for my students. But yeah, I mean, I think that the whole point is there's a lot of people in the open science community who are very happy to collaborate and help. So that that's what I would suggest, is talk to someone who's doing it, and then have them help you set something up to get started, and that does seem to work well.
On Lulu, do I get to specify which day snapshot is represented
Yes.
in that book?
Yeah, this is the third edition, and each edition has its own entry on Lulu.
Okay, so editions aren't every day. There could be a new edition depending on what's in your spreadsheet.
Probably every couple of months we want to put out a new edition. As we implement new things, like the archive, for example, wasn't part of edition 2. So now that we have a preface where we explain the new features, and we just happen to take a new snapshot. But yeah, so that's actually a good question, as how often we do the archiving. I think every couple of weeks or months makes sense at this point.
Fantastic.
Okay, thanks.
we're all scientists, or all of us is thoughtful and diligent in our approach, and some amazing best practices. All right, well, let's take a break. Well, let's start again at 11:30 a.m. sharp, so it gives us about 18 minutes. Grab some coffee and chat with your colleagues. Thank you.